This is lesson 4.4. How many roots or how many solutions does, say, this function have? Well, we know something about this function. We know that it is a parabola. So you might expect it to, let's see, one possibility would be the parabola does this, and it crosses the x-axis in two locations. Maybe the parabola does this, though. Maybe it doesn't have any real solutions, but even in this case, since this is to the second power, it's going to have two solutions. In this case, it would have two real solutions. In this case, it would have two imaginary solutions, but it would have two solutions because it's to the second power. This one, x to the third, we know the end behavior of this graph. This could look a couple different ways. It might look something like this, where it crosses in three locations. It kind of does a John Travolta at the ends. The other way it might look is it might look something like this, where maybe it only crosses once. But even in this case, there's going to be three solutions for this graph. Two of them would be imaginary in this case, and only one would be real, if the graph looked kind of like that. If we look at this graph, x to the fourth, this could look a number of different ways, but it could look something like this, where it crosses in 1, 2, 3, 4 places. It could look something like, this, where it doesn't cross at all, and maybe it has no real solutions, but even in that case, it's going to have 4 solutions. This would have 4 imaginary solutions. This one would have 4 real solutions. And so we can tell by the degree of the polynomial, in fact, our formula theorem, so every polynomial equation with complex coefficients and positive degree has n degree has exactly n roots. So it's very easy to tell how many roots there are. You just look at the degree of the coefficient. You can say, well, there's 4 solutions of some kind. They may not all be real, and that's okay. This is an important theorem dealing with imaginary numbers or complex numbers. So if you have something, a solution of the form a plus bi, then a minus bi is also a root. What that means is this: say you've got one root is 2 plus 5i. This is kind of like, I don't know if you have any friends like this. Do you have any friends who maybe they don't go to the mall alone, they don't really go anywhere alone, and when they do go somewhere, they always bring a friend, and their friend and them always dress alike. They look alike. This is kind of like that. If you have a root 2 plus 5i, well, that root would never be caught alone. They would always have a partner, and so their partner would be 2 minus 5i, someone who dresses like them and likes to go to the mall or likes to go to different places together. So these roots, these complex or imaginary roots always come in pairs. So it doesn't mean all roots come in pairs, but everything that has this imaginary part to it, that will always come in a pair. They always come together. The complex conjugates theorem, that's what it says. If you have a plus bi as a root, then you must have a minus bi as a root. And so if you have a cubic equation, when you read that, I hope you think x to the third power, which means, what we just learned, there are 3 solutions of some kind for this particular equation. So we know 2 of the solutions, where one of them is 5, one of them is 3i. I think we know the third one. This isn't written quite the same form as this, but you can tell this is a complex and imaginary solution. And so I think that this one is always going to have a partner around, negative 3i's with them. If you thought about it, this would be 0 plus 3i. That might make you see easier that this would be the missing solution here. There are 3 solutions for this particular equation. And like we did with other ones, if you want to write the polynomial, if the question was, write the polynomial given these 3 roots, well, let's just go backwards and write the factors. So the factors would be, for this one, it would be x minus 5, x minus the solution. This would be x minus 3i, and this would be x plus 3i. And so to find our polynomial, p of x, or whatever you want to call it. All you have to do is kind of FOIL or multiply these out. The first, I'm going to kind of multiply those two out. And so when you do that, you get, let's see. Okay, let's see, we get x squared minus 3ix plus 3ix. The inside-outside kind of disappear, and then we get minus 9i squared, which is really what? X squared plus 9, because I squared is really negative 1. So negative 9 times negative 1 is positive 9. Don't forget to multiply by x minus 5 here, so we got to multiply that together as well. So now let's FOIL these two, and we get x to the third. Let's see, minus 5x squared plus 9x minus 45. And that is our function. Working in reverse, finding the roots first, then finding the factors, multiplying those to get the polynomial. So very similar to what we did the other day, but this little twist of you had to figure out the third root. We knew there were 3 roots because it was cubic. This looks like a really, really complicated theorem. And you can try to understand this, or you can just kind of, once you start doing this, this is actually a very easy theorem, but it looks so complicated when you look at it in this form. You have to get this idea of P over Q. So P divided by Q, where P are the factors, P represent the factors of the last term, and Q are the factors of the first coefficient. Here's what I mean by that. So if you've got some polynomial like this, I really am keying in on just 2 values here, the first coefficient and the last one. So the last one, let's see, the last one is our P, and the first one is our Q. Well, actually, I should say the factors of the last one and the factors of the first one make up this fraction. So the factors of the last term, that's that term, factors of the first coefficient, which is the Q values there. So let's think about what those would be in this particular problem. So I'm going to think all the possible zeros, or I should say possible rational zeros. Maybe we should clarify that. We're only talking about rational roots here. So we're talking about nice roots, integers, any fraction that can be made up of 2 integers would basically be the type of roots we're talking about. So we're not talking about imaginary roots, we're not talking about irrational or square root type of roots. So let's think about all the values of P that P could be here. So in the top of a fraction, we're going to put factors of 3. So 3 times 1 is 3, so those are the 2 factors of 3 that I see. And then in the bottom here, we're going to put factors of 2, so 2 and 1. So now this makes up a fraction. Let's think about all the different possible combinations we could have from these two values. So we get, let's see, 3 over 2. That's one possible fraction I can make from this. 3 over 1. That's this fraction right here. I could have 1 over 2. And I can have 1 over 1. Now let's clean this up just a little bit here. So we've got, and by the way, we need to add plus or minus to all these. So we have plus or minus 3 halves. This is just 3, so plus or minus 3. This is plus or minus 1 half. And this is plus or minus 1. These are all the possible rational zeros. Now, I know there are only 2 solutions here. If any of those solutions are rational, it will come from this pool of numbers. There's no chance that 5 is a solution or 6 is a solution to this. The reason I know that is because if it's rational, if it's a nice rational, like a nice fraction, nice integer here, it's going to be one of these 8 possibilities here. That's the only possible rational root. So if it says, you know, list the possible rational roots, all you do is, if P over Q, think through all the possibilities, and you write it down. Let's okay, so let's think through this one. And so just like before, we want to think through factors of this divided by factors of this. And so let's make our fraction here. So on top of our fraction is factors of 6. So we have 6, 3, 2, and 1. And the bottom of our fraction would be, why did I highlight that? That's pretty funny. I meant to highlight this. Our first coefficient is here. And so if we look at this one, this would be 3 and 1 are factors of the first coefficient here. So now we have to kind of think through. I just kind of write this just to kind of get my bearings, and I try to think through every possibilities here. So we have 6 over 3. We have 6 over 1. We have 3 over 3. We have 3 over 1. We have 2 over 3. And 2 over 1. And 1 over 3. And 1 over 1. So let's just kind of write these a little bit better. And all of them need to be plus or minus. So this will be plus or minus 2. Plus or minus 6. 6 over 1 is 6. Plus or minus 1. It doesn't matter to me about the order of these, by the way. You can go in any order you want. Plus or minus 3. You just have to have them all listed. Plus or minus 2/3. We're doing fine so far. Plus or minus, oh, I don't need this one. Plus or minus 2. We already have a plus or minus 2 from there. Plus or minus 1/3. And again, I already have a 1 right here, so I really don't need that one. So I've got 1, 2, 3, 4, 5, 6, 12 possible rational zeros. They will come from this pool of numbers. Not sure what this one looks like. Okay, now I actually know what it looks like. I went ahead and graphed it just for fun. And you can see that negative 2.47, which is none of these values, and 0.808, which is none of these values, is where the actual roots for this particular function are. So neither of these roots are rational. I would say these are irrational roots. You can even sometimes look at more digits of that if you need to. But those are not one of these possibilities here. So this particular graph has no rational roots. This theorem only helps us find the nice roots if there are nice roots. There are no nice roots here. These, I would have to figure this out maybe using the quadratic formula. I can figure out exactly what these roots are as far as their exact values, but none of them are these nice rational values here. Find all the possible rational roots and then actually find all of the roots. Okay? So let's figure this one out. Let's figure out all the possibilities here. So I like to list out, I like to write it in a fraction form first. Factors is 16, 8, 4, 2, and 1. And the first coefficient there is 1, so the only possibility there is 1 in the denominator. So I've got plus or minus 16, plus or minus 8, plus or minus 4, plus or minus 2, and plus or minus 1. Okay, so those are all my possibilities, and what I would need to start doing is testing with the synthetic division. I can start testing 1, start testing negative 1, start testing 2. What I'm going to let you do in my class is when this is to the third power, I'll let you get one rational root from the graph. Here's what I mean. So get your calculator out, insert a graph page, and go ahead and type the function. I see part of the function. Not sure where the rest of it is here. Let's try to find out. Ah, now I see it. It looks like it only crosses once here.